Good morning. So we continue the lesson. Today we want to talk about the complex plane and the polar form of complex numbers. Uh, so the idea of the complex plane is very similar to the idea of the coordinate system. The reason is that so far the complex number is an abstract notion that we introduced. So I told you that any number of this form, for example, z, which can be written as a plus b times I, in which uh, a and b are real numbers, and I is a square root of -1, or I squared is -1. Yes? So this is called a complex number, which is an abstract notion, but our brain is probably evolved to understand about pictures better than about abstract things. So that was motivation behind talking about the complex plane. So the complex plane is essentially the coordinate system, but we changed the names a little bit. So for example, so let me just define this. So if you have two axes, one horizontal axis, and then the other one, the vertical axis, with a common origin, which is still I call O. The horizontal one, if it is called RE for real, and then this one is imaginary IM. So that's the only difference. In usual Cartesian coordinates, you say this is the x-axis and this is the y-axis. Here you say that this is the real axis and that's the imaginary axis. And using this idea, every complex number can be represented by a point on this setup, which is called the complex plane, by the way. So when people say the complex plane, you need to imagine two perpendicular axes with the common origin O. The horizontal axis is called the real axis, and the vertical axis is called the imaginary axis. Now, if I ask you, how can I represent this point on the coordinate axis? This is my real part, so you know that we had this before. Do you remember? A is called the real part of Z, and B, if you remember, is called the imaginary part of Z. So if I want to find that point, for example, let us say that here is A, the real part, and here is B, the imaginary part. So this will actually represent a point. That point is Z. Okay, so far complex numbers are just abstract notions, but you can, from this perspective, you can see them as a point on the complex plane. So that's very easy, actually. For example, I can say represent each complex number on the complex plane. Okay, so for example, let me write 1, 2, 3, 4. So for example, the first one, z is equal to 2 plus 3i. Let me call it z1. And the other one, z2, say just -3. z4, say just 3i. And then z5 is -2 minus I. So we want to represent these points on the complex plane. So what we do, we set up a complex plane. The horizontal axis is called the real axis, and the vertical axis is called the imaginary axis. And then I will follow what I just mentioned, yes? So if I want to represent z1, so z1 has real part 2. If you see, this is the real part 2, this is the imaginary part 3. So what I do, the real part is 2, the imaginary part is 3. So if I come here, this point is what we call Z1. And for Z2, the real part is -3, but the imaginary part is 0. So the real part is -3. So hopefully you agree with me that this is just Z2. Yes? What about Z4? Z4 for the real part is 0 and the imaginary part is 3. So this becomes exactly this point. So that is Z. So I don't know why I write like this. Sorry, I have to clean this. This is Z3 and Z4. So this is Z3. And then Z4 is -2 minus I. Where is it? -2. Real part is -2, so it is here. The imaginary part is -1, so it is here. So that's the point here. So that point becomes here. So Z4. Yes? So these are the points that you can represent on the plane. Is that clear? Okay. But there are some exercises in the book that are a little bit more interesting than that. So let me just go to the next page and then give another example. So what we can say represent each given relation. This relation might be equality or inequality, so represent each given relation on the complex plane. So I want you to understand how to read this. For example, number 1, let me start with a simple one. So we say the real part of Z is 2. So what do we mean by this? They are asking represent each given relation. Here the relation is equality. So we want to represent this equality on the complex plane. How you need to read this symbol, it means that you are interested in all complex numbers Z for which this relation holds. So let me just set up a new system for you here. So this is my real axis, and this is my imaginary axis. Okay, so for example, do you think that this point is acceptable? This point is acceptable if what happens? The real part of that point is 2. Is it really 2 or not? Yeah, if you say that each grid is 1 unit, then this is 2. So this point that you see is acceptable, because if I ask you what is the real part of this point, you say it is 2. What about this point? Do you think it's acceptable? Yes or no? Yes, and this point is acceptable. This point is acceptable. This point is acceptable. I don't know, the point in the middle is acceptable, but this point is not acceptable. So if you see, if I imagine all acceptable points, what do I construct? I construct a vertical line passing through that red dot. Yes? So if I ask you to represent this, you will draw this picture for me, this straight line actually. So this is the real part equal to Z. Yes, so you remember, if someone in the complex plane writes this one for you, you need to imagine a vertical line. Okay, a little bit more interesting situation. For example, what happens for this scenario? They say, for example, imaginary part of Z is less than or equal to 3, but for example, strictly greater than -1. So that's a relation. again, you need to interpret it in this way. You are interested in all complex numbers z on the complex plane for which the imaginary part is strictly greater than -1 and less than or equal to 3. Yes? So you need to convince yourself where they are. Yes? So let us set up a coordinate system again. No, sorry, the complex plane. Not they are essentially the same. The names are different. So here, this is the real axis and this is my imaginary axis. Okay, for example, let us try to understand this point by point. So 1, 2, 3. Do you think this is acceptable? Yes or no? If I ask you what is the imaginary part of this complex number, you count them. 1 unit, 2 unit, 3 units. And 3 is acceptable. So yes, this point is one of those points that are acceptable. What about this point? That's also acceptable because the imaginary part is still 3. This is also acceptable. All of these points are acceptable. But what about this point? Do you think that's also acceptable? What is the imaginary part? The imaginary part is a little bit smaller than 3, for example. But that's also acceptable because the imaginary part could be in principle smaller than -3. Okay, so I don't know. You need to convince yourself that how it works. So for example, here, I go 3 units higher and I draw this horizontal line. First of all, I want you to understand that every point on this red line is acceptable because the imaginary point of all those points is exactly equal to 3. But that's not the whole story. So what about this limit? I cannot go below -1, okay? So imaginary part -1 is where? So for example, here. But then you need to show that you are respecting that this is not included by drawing a dotted line or a dashed line, yes? So this means that by drawing this dashed line, you show that you know that imaginary z equals to -1 is not acceptable. So this means that by doing this, you are excluding these points from this relation. But is this the only picture? No, because imaginary part should be somewhere between these two lines. So I don't know if I want to highlight them. If I can use a trick here, I don't know if I can use that, but it does not work because this will fill up the other. Yes, but then how should I do that? I can use this trick probably to make a dashed line, yes. Something like this, yes. Anyway, so everything here, of course, this is not, let me clean this because there is no restrictions here. They should continue forever. So this is the picture that I want you to understand. Yeah, is that understandable? So you need to have a picture about what is going on. So if I ask you what is this relation represent, you will tell me that this represents a strip, including one border line, excluding the other border line. But everything in between is also acceptable. Okay, so that is one idea that you need to know. Another idea is that we can represent every point by a vector, which is also important for the next part of the lesson. So let me go, and that's also very simple. So let me go to the next part. So representing complex numbers with vectors. Okay, so this is a subtitle we can give it here, but that's also very simple. So let us say that I give you a complex number z, which is a plus bi. Okay? And then you know that on the complex plane, meaning that if you have your real part here, real axis here, and then you have your imaginary axis here, and then you can for example, let us say this is A, and let us say this is B. And then you know that you can find that point on the complex plane. It will give you this, for example, point. The vector that you draw from the origin to that one, to that point, and then put the arrow here, this is also a good representation. Sometimes people use vectors to represent complex numbers. So this yellow vector that you see here represents this complex number. Yes? And there are some terminologies related to this vector that we want to introduce. One of them is the notion of absolute value. Okay? This length, so absolute value of z, so let me write definition here. So let z be a complex number the distance from the origin to z on the complex plane is the absolute value of z, and is denoted by just the same symbol that we use for absolute value in real numbers. Yes, that is the absolute value. So if I want to show it on the picture, you would say that, okay, this length that you see here, this length is the absolute value of z. Can I find a formula for the absolute value of z? The answer is yes. So because you can use the Pythagoras theorem, you can say the absolute value z, which is this length to power 2, is this length to power 2 plus this length to power 2. So this is also good to know that absolute value of z, the absolute value of z is equal to the real part of z, whatever it is, to the power of 2, yes, plus the imaginary part of z to the power of 2. And then, of course, you have to take a square root, because by Pythagoras theorem, it gives you the hypotenuse is squared. Of course, if I want to make it symbol for this number, the real part is a, the imaginary part is b. So if you want to, in this case, you can write square root of a squared plus b squared. Yes? That is something that's very easy. But let us just do some practice here. Remember, if someone asks you what is the absolute value of a complex number, it is the distance from that point to the origin. Okay? And if you can understand it by imagining the picture, you can immediately write the answer. Otherwise, if that's a little bit hard, we have to use the formula to calculate this. So let me give a very simple example. Example, determine the absolute value of the complex numbers, of the given complex numbers Okay, so for example, number 1, let me write z to be z1 to be say So 3 plus 4i. Okay, so let us just do case by case. So if I want to calculate the absolute value of z1 here, because it is not that easy to guess, let me just try to actually use the formula. So the formula is a square root of the real part squared. The real part is 3 squared plus the imaginary part squared, which is 4 squared. And then this is very simple now, yes? So this becomes square root of 9 plus 16, which is the square root of 25, and that is 5. It means the distance from this point to the origin should be 5 length unit. So part 2, if I just give you z2 to be minus 5i, okay? You can imagine in this case, where is minus 5i? So if you want, you can imagine it to answer, but it's possible also to calculate. So if this is my imaginary axis, so where is that point? That point is minus 1, minus 2, minus 3, minus 4, minus 5. So that point is here. Yes? So if I ask you what is the absolute value, it is the distance or the length of that vector, yes? And then what is this length or what is this distance? It's 5 units. So it's very clear that the absolute value of z2 should be simply 5. But if I want to use the formula to calculate this, that's also possible. So what is that? This is square root of the real part, which is 0 to power 2, the imaginary part, which is minus 5 to the power of 2. And the answer becomes square root of 0 plus 25, and then hopefully you know that the answer is as you predicted, 5. So it doesn't matter how you want to calculate that. So that's the distance. Is that clear? Okay, we also have another idea related to complex numbers, and that is the notion of the argument of the complex number, okay? And that is, if you don't mind, let me go back to the previous slide and do it here. This angle that this vector makes with the positive part of the real axis is called the argument of your complex number. Okay, so let me show it with, for example, theta. Theta is called the argument of z. Okay, and is denoted by ARG, argument of z. Of course, there are two conventions here. One convention is you go on the interval from 0 degrees to 360 degrees, or some convention is that you go from minus 180 to 180, yes? If you go from 0 up to 360, I hope that you agree with me that we cover all the range, yes? If we go from minus 180, here is minus 180, and we go to 180 again, so we still cover the whole range. But I think for high school, it's better to use the first convention. So we stick to this fact that theta is somewhere between 0 degrees and 360 degrees. And then here, by convention, we decide to include this, exclude that, because it doesn't matter. 360 degrees and 0 degrees are on the same real part. So by convention, they have chosen to give it 0, okay? Either you should include this one, or exclude this, include this one. And of course, you can also express it in radians. So it is from 0 to 2 pi if you want to express it in radians, okay? Okay, so might be you are asking why these are important, because you see if the title, we want to talk about the polar form. Okay, that's yeah. We want to talk about the polar form of the complex number. This is why we need these concepts, the concept of the absolute value and the concept of the argument. Okay, so let us do some practice to give you some complex numbers and ask you for determining the argument. Okay, this is simple, but there are some technicalities. Let me make sure that you know what to do. Okay, so let us start with an example. Determine the argument of the given complex numbers. So number one. So if I say, for example, z1 is 5. So what is the argument of that? The first thing that you need to do is to approximately at least locate the location of the point and try to draw the vector corresponding to that, yes? So if this is my real axis and this is my imaginary axis, where z1 is located, 1, 2, 3, 4, 5. So here is z1. And then you draw the vector and then you determine the angle. So what's the angle? What's the angle between the red arrow and the pink horizontal arrow? 0. Of course, you can say it's 360 degrees, but by convention, we include 0 and exclude 360 degrees. So it is very clear that the argument here of z1 is just 0. Yes? Now, let us go to the next one. If I tell you, for example, z2 to be square root of 3 times I, okay? You want to find the argument of this one. Again, what you do, you try to locate that point somehow on the complex plane. Yes, so this is the real part and that's the imaginary part. So the real part is of course 0, but the imaginary part is a little bit, is bigger than 1, smaller than 2. So for example, let us assume that's here. Somewhere here. So let us assume that this is a square root of 3. But the point is that if you draw the vector, so this is your vector. And then what is the angle? What is that angle? 90 degrees. So that is your theta. And if you want to express it in radians, you can say that the argument of z2 is pi over 2. Or of course, if you write 90 degrees, that's also quite acceptable, depending on the problem. Yes? Okay, so let us give another example. So number 3, for example, let me write z3 to be minus, for example, 2i. Okay, so what is that one then? We need to somehow locate the point. This is the real part, and that is the imaginary part. Yes? And that is minus 2. So it should be here. because the real part is 0, the imaginary part is -2. So this is the vector for Z3. But then remember, you need to measure this angle now, which is your theta. So what is that one? It's 270 degrees, and if you want to express it in radians, so it becomes 3 pi over 2. Yes? I give you 2 more examples. So number 4. So for example, Z number 4 is equal to 1 plus I. So we want to find the argument of this. Again, we have to locate the point. So what is that? So we draw this to make it more clear. So let me make it a little bit larger. Let us assume that this is 1 unit. Okay, so then this is also I. Yes, that's also 1 unit. So if you locate the point is here. And if you draw this vector, this is your vector. And this is just Z4. And then you realize that what you're supposed to tell me is this angle, which is theta. So what's that angle? Pi over 4. It's 45 degrees, yes? So arc of Z4 is pi over 4. Okay, and then one more example here. So let me write Z5 equals to -3 minus square root of 3 times I. Okay, so we want to find that one. So here is the real axis, and here is the imaginary axis. Okay, so -3, let me make it a little bit larger. So -3, so assume that this is -1, -2, and -3. That's the real part, and minus the square root of 3 is somewhere here. You don't need to be very precise, you just need to motivate to find in which quadrant it is lying. So if that's the case, so if I give you this is minus the square root of 3 and this is -3, and then you see that this is the vector representing your complex number. So that is Z5. But then remember, you are supposed to calculate this angle. Okay? So that angle which we call theta. Okay, if you want to calculate this angle, what you can do, I prefer to do it in this way. For example, I will concentrate on this angle, which is an acute angle, or if you want on this angle, it doesn't matter that much. For example, let me call this angle to be alpha. And then I ask myself, can I calculate tangent of alpha based on the information that I have? The answer is yes, because tangent of an acute angle in a right angle triangle, I concentrate on this right angle triangle here, and tangent of alpha is the length of the opposite side, which I know. Don't write negative because you want to calculate the length. The length is the square root of 3 divided by the length of the adjacent side, which is 3. Okay? Okay, if this number is famous or is it in the table, you can just read alpha. Otherwise, you use your calculator to calculate tangent inverse and calculate alpha. Yes, but this is one of those numbers that I have in my memory. So tangent inverse of a square root of 3 over 3 is 30 degrees. So this means that alpha is 30 degrees, or if I insist to express it in radians, it becomes pi over 6 radians. Okay, it's better not to put it in a box because that is not supposed to be my answer. My answer is supposed to be delta. Sorry, theta. So what is theta then? So argument of Z5 is theta. But what is theta? So you see theta is from here to here, which is 180 plus alpha more. So I have to add pi to what I got before, which is pi over 6. And if you calculate that, it becomes 7 pi over 6. So that is the argument of this complex number. Is that clear? Okay, so but sometimes if the numbers are not good, so you don't have it in table, you have to use the calculator. Okay, that's it. But why we are interested in this, the logic is a little bit weird, because usually in mathematics we have the tendency to make things simple. But here, this is the first time that we want to make things a little bit complicated. It means that I want to discuss about the polar form of complex numbers. Or if you want another name, we can call it trigonometric form. So for example, let me just tell you why this is a little bit complicated. For example, I give you a complex number as simple as I. Then if I ask you to write the polar form of I, you need to write I as cosine of pi over 2 plus I sine pi over 2. Okay? First of all, I want you to understand this is immediately understandable, because if I ask you what is cosine of pi over 2, you tell me 0. If I ask you what is sine of pi over 2, you tell me 1. So really the right-hand side is I. But you might, and this I call the polar form or trigonometric form of I. And apparently you see that I is the simple innocent creature there, but we are making it look like devil, yes? But what is the point? The point is that there is a payoff here, because the polar form of the complex number will help you to raise the complex numbers to high powers fairly simple. For example, if, of course, in this case, high powers of I are not that hard, because I squared is -1, and then you can use this fact to even calculate high powers of I. But for example, let me just give you this number, z, to be 1 plus 3, or the one we actually calculated just right now. For example, I give you -3 minus the square root of 3i. This is called the standard form or the Cartesian form, yes? If I ask you to calculate z to power 100, then what you are supposed to do, in principle, that's not a hard task. You just write -3 minus the square root of 3i to the power of 100. And then in principle, this is the obstacle in front of you, because that's a binomial. If you want to raise it to power 100, either you need to use the binomial theorem that you learned in Math 5, which is also not that easy because it includes 101 terms, or you need to write this 100 times and start multiplying it. So that is the reason that we momentarily make this harder by writing it in trigonometric form, and then you will see that in trigonometric form, raising these numbers to high powers are fairly simple. So still, in mathematics, we prefer to make things simple, but the reason that we make it a little bit complicated, apparently, because we gain something in return. To calculate something much harder, very simple. So that was the motivation of why we want to do it, okay? So this question is still left open. We'll probably come back and answer this later. But today we want just to learn how to put a complex number in its polar form. That's the idea. And that's also very easy to understand. So for example, let me just show you what we want to do. So assume that this is the real axis and this is the imaginary axis. And let me my complex number be z equals to a plus bi. Okay, so let me just show this. For example, let us say that this is your vector representing that complex number z here. So then this means that this is a and this is b. Okay? And then if I ask you what is this length, you already know. What is this length? Is the absolute value of z, yes? Okay, let me change my color. So this length is absolute value of z. And if I ask you what is this angle, let me call it theta. But of course, you know theta is what is called the argument of z. Now, let us concentrate on this triangle. Yes? Okay, so if I ask you what is cosine of theta, what is your answer? So cosine of theta is equal to the adjacent side divided by the hypotenuse. So this becomes what? A over absolute value of z. And if I ask you the same question for sine theta, it will tell me it's the opposite side, but the opposite side has this length, which is b. So it means b divided by the hypotenuse, which is the absolute value of z. Okay, from here, what you can conclude, instead of a, you can write absolute value of z times cosine theta. And if I ask you what can you write instead of b, you will tell me that b is equal to absolute value of z times sine theta. And then what I do, I will take this one and put it here, and I will take that one and put it here. Okay, so then what happens, then z becomes absolute value of z cosine theta plus I, or let me write I later. Instead of b, I put absolute value of z sine theta, but I have a multiplication by I. And then what you can see, I can factor absolute value of z out. And then what I gain is cosine theta. And if you don't mind, let me put I on the left this time. I times sine theta. And usually it is common in complex numbers, people denote this by r. So the absolute value is denoted by r. So in that case, I can replace this one with r. And then this is what we want to write. So z is equal to r cosine theta plus I sine theta. If someone asks you what is r, you will tell me that r is absolute value of your complex number. And if someone asks what theta is the argument of your complex number. This is called the polar form of your complex number. Yes, the polar form of z. So I will not continue teaching about what is it useful for, but I want you to learn how to put a number which I give you in the polar form. The application will be the topic of the next lesson. After the break, we will have it. Any questions so far? So you see that this for our eyes, This is much simpler than this one, because this one is already freaking, yes, because it's involved with trigonometry. But I will tell you what is that one. So if you want to calculate this one, it's very, very hard. I mean, it contains 2 to the power of 100 terms if you want to just multiply them, but you will see that we can calculate this using this idea, very simple. Any questions? Okay, so I want to give an example. For example, this is something you need to know. I give you this number and I ask you to put it in the polar form. So what you need to calculate, you need to calculate the R, which is the absolute value, and based on what we learned. You also need to determine about the argument, as we did, and just put them in the formula, but do not simplify them anymore. Because if you simplify them, you get back to this exactly like here, you see? If I ask you to simplify the right-hand side, of course you go back to I, because cosine of pi over 2 is 0, sine pi over 2 is 1. But you have to keep it in its polar form. Okay, so remember, I just want to tell you this number that I have it here. I don't want to repeat this. So in principle, this part is the solution to this problem. I have already calculated theta. So theta is 7 pi over 6. I want to use this information. So let me give an example here. Right, z equals to minus 3 minus square root of 3i from the previous example. In polar form. Okay, so the first thing I have to, let me write the formula here in front of you. So let me just, I can copy and take it with me there. Okay. It's here. Okay, so this is the polar form formula. So what do I need here? I need 2 ingredients. One is R, which is this, and 1 theta, which is the argument. So, okay, the first thing that I do, I calculate R. But R is absolute value of Z. But for absolute value of Z, we learned the formula. Do you remember? It was the square root of the real part here is minus 3 to power 2 plus the imaginary part, which is minus the square root of 3 to power 2. Yes, and then this becomes the square root of 9 plus 3, which is the square root of 12. It doesn't matter, but I prefer to write it as 2 square root of 3, yes? Because 12 can be written as 4 times 3. Square root of 4 is just 2. Okay? We already saw that. What was theta? Do you remember? It was 7 pi over 6 from the previous problem. So this means that the polar form is z equals to, instead of r, I put this number, which is 2 square root of 3, and then you open this pair of brackets, and then you write cosine 7 pi over 6 plus I sine 7 pi over 6. So this is the answer we expect you to write. And you see this is much harder than this original one. Okay? And of course you can do whatever you could do with trigonometry. That is enough. But for example, if from trigonometry you know that cosine 7 pi over 6 can be written as, I don't know, cosine pi plus pi over 6, and it becomes minus cosine pi over 6. Something like that. and the sine 7 pi, or it is not necessary, but I mean, whatever you learned in trigonometry, you can apply here as well. So for example, if you want to, you can replace these with these numbers, but of course you will have a negative sign. But that is not a polar form, remember. Because if you put a minus sign here and minus sign here, I can pull this minus sign and I'll put it here. When I say a polar form, I want you to see that this is an absolute value, so it is not negative. So this is why this is the polar form. But I'm telling you, from calculational point of view, if you want to replace them with that, that's completely okay. Any questions? Okay, so the only downside about this lesson is that you still don't know why putting in polar form is good for in practice, even though I explained that for you. So if someone asks you if you want to summarize, you would say that if I want to raise a complex number to high power, the polar form is preferable, as we will see in the next lesson. Any questions? No? Okay, thank you.